Okay, so I want you to try and picture this. Just imagine you're holding a very specific piece of chrysoberyl, right, in your hand.
Right, a raw gemstone.
Exactly.
Yeah.
And you're standing completely outside. It's high noon, clear sky, and you are just exposed to the totally glaring, unmitigated black body radiation of the midday sun.
The full spectrum.
Yeah. And in your palm, this crystal, it looks like a vivid, just breathtaking emerald green. I mean, it looks entirely stable. It's a green rock.
Which is what you'd expect, right?
Right. But then you take that exact same stone and you just walk indoors. You step into a room that's lit by, say, a couple of tungsten light bulbs or even just some candles.
So a much lower temperature light source.
Exactly. And instantly, the optical properties of the stone they completely invert. The green is completely gone, wiped out. You are now holding a deep, smoldering ruby red gemstone.
Which is just, I mean, it's wild to see in person.
It really is. It feels like it completely defines our baseline assumptions about, material permanence. Like, things aren't supposed to just change color because you walked into a different room.
Yeah, we definitely operate on this assumption that a material's inherent properties, like its absorption and its transmission spectra, are, well, they're static. Unless you chemically alter the thing or heat it up until it melts, it should stay the same.
Exactly.
So when you watch a mineral physically shift from green to red simply by walking through a door, it feels like a total violation of physics. But it's actually not magic at all. It's a highly localized, incredibly rigorous calculation of light absorption that's just reacting to a changing ambient field.
And that's what we're getting into today. Welcome to today's deep dive, where we are doing a complete forensic examination of this optical illusion. In mineralogy, it's known as the Alexandrite effect.
It's a fascinating topic.
It really is.
Yeah.
And our mission today is to completely map out the hidden physics of this color change. We are going to track exactly how specific photon energies interact with these tiny chromium ions embedded in a rigid atomic lattice.
Because we want to prove that this macroscopic optical illusion, the thing you can see with your naked eye, is actually driven by entirely invisible electrostatic forces, forces that are altering electron transitions on a quantum level.
Right. We're going way beyond the gemological novelty of it. We're getting into the quantum mechanics of the crystal field.
Okay, let's unpack this.
Yeah.
Because the mechanics here are actually remarkably elegant, aren't they?
They really are, yeah.
Yeah.
Once you isolate the specific variables, it makes perfect sense. We're basically looking at this precise three-way collision.
Between what?
Between external spectral power distributions, human neurobiology, and the exact geometry of subatomic electron clouds.
Wow. Okay.
Yeah, I mean, it's a phenomenon dictated entirely by the strict rules of quantum electrodynamics. The stone itself isn't actually doing anything active. It's completely passive. Okay, so to really grasp that, I feel like we have to start by analyzing the macroscopic environment first. Yeah, before we shrink down to the atoms. We have to look at the stage this trick is played on, the interaction between the light source, the mineral filter, and your own brain.
That's the perfect place to start because it's really tempting to just think of white light as this one monolithic thing. Like light is just light.
Right. Daylight looks white. A light bulb looks white-ish.
Exactly. But when you step from the outdoors, which is bathed in the 6,500 Kelvin blackbody radiation of daylight, into a 2,856 Kelvin incandescent room, you are fundamentally drastically altering the actual spectrum of light hitting that crystal.
You're basically changing the menu of photons available in the room.
That is a great way to put it, yes. Daylight at 6,500 Kelvin, it has an emission spectrum heavily weighted toward the shorter, higher energy wavelengths.
The blues and the green.
Right, lots of blue and green photons raining down. But incandescent light, on the other hand, is completely skewed toward the longer, lower energy wavelengths.
The reds, the oranges, the yellows.
Exactly, with almost a complete lack of blue light. So the environment is completely different. And the stone itself, the Alexandrite, it possesses what we call a highly specific dichromatic transmission spectrum.
Okay, break that down for me. Dichromatic transmission spectrum.
It basically means it acts as an optical filter with two distinct, very narrow windows where it lets light through. There's one window open in the red region and one window open in the blue-green region.
Which means, by definition, it has to have a massive absorption band sitting right in the middle, dividing those two windows, right?
Yeah.
Like an equalizer cutting out the middle frequencies of a song.
Yes, that is exactly what it is. And that critical threshold is a massive absorption peak centered exactly at 570 nanometers.
And 570 nanometers, that sits squarely in the yellow-orange domain of the visible spectrum.
Right, so it basically acts as this giant spectral wall. The stone absorbs all that mid-spectrum energy. It just eats the yellow and orange light, and it only permits the high-energy blue-greens and the low-energy reds to actually pass through to your eye.
Okay, so if the stone is just an optical equalizer filtering out wavelengths, why does it completely switch colors instead of just looking, I don't know, darker? Is the stone actually doing anything?
No, that's the crazy part. The physical absorption process happening inside the crystal lattice is completely identical in both environments. The stone doesn't change.
It's just sitting there.
It's just sitting there.
Yeah.
In daylight, the ambient light source is flooding the stone with blue and green photons, right?
Because daylight is mostly blue and green.
Exactly. So those blue and green photons hit the stone, they find that blue-green transmission window, and they just pass right through the lattice completely unhindered and strike your retina.
So you perceive green.
Right. The stone is literally just reflecting the dominant energetic state of the environment.
Okay, so when you move indoors.
When you move indoors, you turn on a lamp, and suddenly those blue and green photons are just largely absent.
Right, because incandescent light is all red and yellow.
Exactly. The ambient field is now totally saturated with red photons, and those red photons pass right through the stone's red transmission window, while the yellow ones hit that 570 nanometer wall and get absorbed.
So only the red makes it to your eye and you perceive red?
Yes. The stone is just a binary reporting mechanism for whatever light is in the room. What's fascinating here is that the exact same photons are being absorbed in both places. We are literally just changing the menu of what's available to bounce off it.
Okay, that makes sense on a physics level, but that alone doesn't explain why the visual shift is so violently jarring.
What do you mean?
Well, if I look at a blue shirt, like under a slightly yellow street lamp, it doesn't suddenly turn stark red. It just looks like a slightly washed out, desaturated blue. I still know it's a blue shirt.
Oh, I see. Right.
So the missing variable here has to be the human visual system, right? Specifically, how our brains are being tricked.
Yes, absolutely. It's a failure of our color constancy algorithms.
Color constancy. That's the neurocomputational software your brain uses to basically normalize the color of objects even when the lighting changes, right?
Exactly. If we didn't have color constancy, a standard piece of white paper would consciously look blue to you at noon, and it would look bright orange at sunset.
Which would be totally disorienting.
It would be impossible to navigate the world. So your visual cortex is constantly, continuously calculating the ambient illumination and essentially subtracting it from the color of the object you're looking at.
To give you a stable baseline.
Right. It normalizes the world for us, and it operates flawlessly for almost all materials, especially at normal viewing angles.
But the Alexandrite effect effectively hacks that software. It breaks the algorithm.
It completely breaks it, and we can actually see why if we map the colors mathematically.
Okay, lay the math on me.
So if we map the daylight color and the incandescent color of this specific stone in what's called the C-Lab color space.
C-Lab, right.
Yeah.
That's a three-dimensional grid scientists use to map human color perception.
Yes. In this 3D model, the axis represents the green-red opponent channel, and the bottom axis represents the blue-yellow opponent channel.
Okay, so green and red are on opposite ends of one axis.
Exactly. So when an Alexandrite stone shifts from daylight into incandescent light, its mathematical coordinates on that axis cross the origin entirely. It moves from a deeply negative value, which is green, to a highly positive value, which is red.
Oh, wow. So it's not just a subtle shift.
No, that traversal across the origin represents a hue angle difference of approximately 180 degrees.
They are absolute opponent colors.
Exactly. The shift is so computationally massive that your brain's color constancy algorithms simply cannot bridge the gap to normalize it.
So your visual cortex just gives up.
Pretty much. It's forced to abandon the baseline and just register a complete instantaneous state change. You see it flip from green to red because your brain can't do the math fast enough to average it out.
The brain concedes defeat to the crystal. I love that. Okay, knowing how the external light is filtered by that 570 nanometer absorption wall, it really brings us to the actual architecture of the filter itself.
The atomic structure.
Right, because if the stone is just a passive stage, then the composition of that stage is what dictates that exact 570 nanometer wall. We have to shrink down and look at the actual chemistry of the Chrysoberyl lattice.
And this is where it gets really chemically interesting because pure Chrysoberyl, which is beryllium aluminate, Bl2O4 tols, is completely optically transparent.
Wait, really? It's just clear.
Completely clear. It possesses no inherent color centers at all. It looks like glass.
So you're telling me this incredibly rare, super expensive color changing effect is caused by an impurity, like a defect in the crystal.
That's exactly what it is. The Alexandrite effect is derived entirely from a trace chemical contamination that happened during the crystal's geological formation millions of years ago.
What kind of contamination?
Chromium. Less than 1% of the aluminum ions, the A3 plus ions in the lattice, get isomorphically replaced by chromium ions, specifically Cr3 plus plus.
Less than 1%.
Less than 1%. And that tiny fraction of a percent of chromium is generating that entire massive 570 nanometer absorption wall.
It is. I mean, transition metals like chromium are known for their incredibly strong interactions with visible light, but the efficiency of this specific atomic substitution is just staggering.
Okay, so to see how that trace impurity is dictating the macroscopic optics, like what we see in our hand, we have to isolate a single chromium ion inside that lattice and look at the quantum physics.
Right. We have to look at the electron transitions. So when that 2psi3 plus Lionel sneaks in and replaces an aluminum ion, it finds itself sitting in a very specific geometric constraint.
A physical cage.
Exactly. It occupies what we call an octahedral coordination site, meaning that one central chromium ion is surrounded perfectly by 6 oxygen ions, O2 forming a rigid, 8-sided octahedral cage. Okay, I'm picturing it. Chromium in the middle, 6 oxygens forming a cage around it.
That specific geometric configuration is the crucible where all this optical physics happens. The chromium ion has electrons hanging out in its d orbitals in a resting low-energy state. Quantum chemists designate this as the 4A22 ground state.
And then light enters the picture.
Right. When a photon of light with a wavelength of exactly 570 nanometers propagates through the crystal lattice.
Because its energy corresponds perfectly to the gap between that ground state and the next level up.
Exactly. The energy of a 570 nanometer photon perfectly matches the gap between that 4A22 ground state and the excited 4T22 state.
So the chromium electron just absorbs the photon, uses the energy to make that quantum leap up to the 4T22 excited state, and boom, that specific slice of yellow-orange light is completely deleted from the spectrum.
Yes. It's consumed as fuel for the quantum leap. And the size of that specific energy gap is the sole dictator of exactly where that absorption band sits.
Okay, but this leads us directly to a massive contradiction, doesn't it? What mineralogists refer to as the gemstone paradox.
Ah, yes. The paradox. It's a great mystery.
Because if chromium in an octahedral cage causes this specific 570 nanometer wall, what about other precious gems? Like ruby. Ruby gets its intense red color from the exact same Cr3 ions plus impurity, sitting in the exact same octahedral cage of 6 oxygen ions, just substituting for aluminum in a corundum lattice.
Right, and emerald gets its brilliant green color from the exact same CCR3 plus octahedral setup, just in a barrel lattice.
Exactly. If chromium's the singer and the 6 oxygen atoms are the acoustic shell of the stage, shouldn't the concert sound exactly the same every single time?
You would think so.
Why is ruby always permanently red and emerald always permanently green and alexandrite sits right in the middle doing both? If the immediate atomic setup chromium surrounded by 6 oxygen atoms is identical, the localized crystal field should be identical. The absorption gap should theoretically be exactly the same.
Right, which means the variable that's actually dictating the color change has to be spatial. It has to be related to distance.
Right, and that was the prevailing scientific consensus for decades, wasn't it?
Oh, absolutely. If you go back and review the gemological literature from the 1980s, the operational theory relied entirely on the physical distance between that central chromium ion and its 6 oxygen neighbors.
It was a purely thermodynamic and electrostatic argument, which honestly makes complete sense under classical models.
It does. The thinking was, if the oxygen ions are physically closer to the chromium ion, their negative electron clouds are going to exert a much stronger repulsive force on the chromium's electrons.
It's like pushing 2 negative magnets together.
Exactly. And that intense electrostatic repulsion would increase the energy required for the chromium electron to make the leap to the excited state. The physical crush of the cage widens the energy gap.
And a wider energy gap requires a much higher energy photon to actually trigger the transition.
Right. So the 1980s textbook stated that in a ruby, the average distance between the chromium and the oxygen atoms was super compressed, like 1.913 angstroms.
Tiny.
Very tiny. And because of this compressed bond length, the heightened electrostatic repulsion shifted the absorption band way up into the higher energy blue and green regions.
So the ruby absorbs all the blues and greens and leaves only the low energy red light to bounce back to our eyes. Hence, Ruby is red.
Exactly. And conversely, the old theory held that in an emerald, the chromium to oxygen distance was significantly longer. The cage was looser.
So the oxygen atoms exert less repulsion, the energy gap narrows, and the absorption band drops down to the lower energy red and yellow regions, permitting the high energy green light to pass.
Leaving the emerald green, it was an incredibly elegant model. It perfectly aligned with everything we could observe on a macroscopic scale.
But it was wrong.
It was completely fundamentally wrong.
I love when that happens in science. The shift in our understanding arrived pretty recently, right? Around 2012.
Yes, 2012. And it was driven by the application of some highly advanced analytical techniques. Specifically, EXA-FS spectroscopy combined with density functional theory calculations.
EXA-FS, that's extended X-ray absorption fine structure.
Right. It's an incredibly precise way of measuring atomic distances.
Because with EXA-FS, you basically irradiate the sample with tunable X-rays, right? The central chromium atom absorbs the X-ray and ejects a photoelectron. And that photoelectron ripples outward like a spherical wave, bounces off the surrounding oxygen atoms, and backscatters back to the chromium.
It's essentially atomic sonar.
Yes, atomic sonar. And by analyzing the quantum interference pattern of those outgoing and incoming waves, you can calculate the exact radial distance of the neighboring atoms. EXA-FS doesn't rely on theoretical models. It's a direct, highly precise atomic ruler.
And when the 2012 research teams actually applied the EXA-FS ruler to ruby and emerald lattices, the data completely dismantled the 1980s distance theory.
What did they find?
They found that the mean distance between the chromium ion and the surrounding oxygen ions in a ruby is 1.97 angstroms.
Okay.
And the mean distance in an emerald is exactly 1.97 angstroms.
Wow.
The bond lengths are practically indistinguishable. The margin of error is statistically irrelevant to the massive optical differences between the stones.
So the textbooks were wrong. If the chromium-oxygen distance is identical at 1.97 angstroms in both stones, then the repulsive force from the cage is a constant. The immediate atomic walls of the room are not dictating the shift in the absorption band.
Right, which created a massive crisis in the field, a huge paradox. If the primary coordination sphere is identical, the electrostatic force dictating the color has to be originating from outside the immediate oxygen shell.
Here's where it gets really interesting. We have to map the non-local potentials.
Yes. We have to look at the invisible architecture of the whole neighborhood, not just the single room. And this is precisely where researchers brought in density functional theory, or DFT.
To map the internal electric field of the broader crystal lattice.
Exactly. To understand how DFT works here, we have to look at the Hohenberg-Kohn theorem, which is the foundational principle of this math.
Okay, bear with me. Let's break this down.
The theorem basically states that the ground state properties of a many-electron system are uniquely determined by an electron density functional.
Right, because otherwise trying to calculate the traditional Schrödinger equation for every single interacting electron in a macroscopic crystal would be impossible. The math would take forever.
It would be computationally impossible. But DFT gives us a shortcut. It allows us to mathematically map the overall electrostatic potential, which they designate as VVOR, generated by the entire arrangement of the rest of the lattice ions.
So we aren't just looking at the 6 oxygen atoms anymore. We are calculating the electrostatic influence of the next nearest neighbors. The beryllium, the silicon, or the distant aluminum ions that sit way outside the immediate oxygen cage.
Right, because even though they are spatially further away, their electrical charge still projects through the lattice, penetrates the octahedral oxygen cage, and warps the energy state of that central chromium ion.
That non-local potential, that VRR, is the invisible architect of the Alexandrite effect.
It really is. And in quantum chemistry, the specific size of that energy gap between the ground state and the excited state is quantified by something called the Lagrange field splitting parameter.
The 10dq.
Yes, 10dq. The size of 10dq literally dictates the exact wavelength of light the ion will absorb.
So the investigation entirely shifts to how the internal electric field of the broader lattice warps that 10dq parameter. Let's look at the corundum lattice of a ruby first to see how it works in practice.
Okay, so corundum possesses what crystallographers call a C3-point group symmetry.
Which means?
It means the arrangement of the distant aluminum ions around the chromium site is very lopsided. It generates an internal electric field that is highly asymmetric along the primary axis.
So this asymmetric non-local field is basically exerting a highly uneven electrostatic pressure on the chromium ion. It's squeezing it weirdly from afar.
Exactly. It uniquely warps the spatial distribution of the chromium's outer orbitals, specifically the Heika antibonding orbitals. And the DFT calculations reveal that this specific asymmetrical warping artificially inflates the 10DQ gap.
By how much?
The asymmetrical field increases the gap by exactly 0.24 electron volts.
And 0.24 electron volts, optically speaking, is massive.
It's a huge jump.
It pushes the entire absorption band higher up the visible spectrum, completely wiping out the blue and green transmission and locking the stone in as a pure red ruby. The asymmetric electric field from the distant ions is actively restricting the electrons from jumping.
Yes. Now compare that highly compressed asymmetrical setup to the barrel lattice of an emerald,
which operates under D3 point group symmetry.
Right. When DFT maps the internal electric field of an emerald, it reveals this amazing phenomenon of almost perfect electrostatic cancellation.
Well, this part is brilliant.
It's so cool. So outside the immediate oxygen complex of an emerald, there's a shell of positively charged beryllium ions, B22 plus $.
Because beryllium ions are exerting a potential trying to warp the chromium's orbitals, just like in the ruby.
But positioned precisely in the next coordination shell outward are silicon ions, C∅R plus $.
And the scalar field projected by those distant silicon ions perfectly mathematically counteracts the field projected by the closer beryllium ions.
It's a structural neutralization. They basically cancel each other out. And because the broader lattice field cancels itself out, the central chromium ion in an emerald experiences almost zero external electrostatic warping.
So the D3 symmetry results in a negligible shift of that 10DQ parameter. It's like a minuscule reduction of only 0.05 electron volts, right?
Exactly. Without that massive asymmetrical compression we saw in the ruby, the energy gap in emerald remains relatively small. So it absorbs the lower energy red and yellow photons, which leaves the high energy light to pass, locking the stone in as a pure green emerald.
Which perfectly isolates Alexandrite, because the Chrysoberyl lattice doesn't possess the extreme asymmetric compression of the ruby, but it also doesn't achieve the perfect electrostatic cancellation of the emerald.
Right, it sits right in the middle. Its internal electric field places the 10DQ parameter in this exact, highly calibrated Goldilocks zone.
The non-local electrostatic potential forces the energy gap to produce the precise 570 nanometer absorption wall, which is what enables those dual transmission windows we talked about earlier. The whole magic trick is caused by distant ions just passively existing in a specific geometry.
Exactly. And, there is actually one final hypothesis in the scientific literature regarding this mechanism that we should probably clear up.
Oh, the delocalization myth.
Yeah, the charge transfer idea. Some theoretical models a while back suggested that these non-local lattice potentials were actually inducing a physical charge transfer.
Meaning they thought the unpaired electrons of the chromium ion were actually bleeding out of the oxygen cage and flowing into the surrounding lattice.
Right, and that this delocalization was what altered the 10DQ gap. Like the electrons were stretching out.
But the empirical data doesn't support that at all, does it?
Not even a little bit. The electron nuclear double resonance results. Yes, Endor spectroscopy. It definitively tracks the spatial mapping of those unpaired electrons. And it proved, beyond a shadow of a doubt, that the unpaired electrons remain strictly confined within the octahedral complex.
They stay inside the cage.
They absolutely do not flow into the broader lattice. The color shift is an entirely localized optical reaction to a non-local electrostatic field. The electrons remain stationary, but the energy required for them to jump is warped by the invisible architecture of the crystal.
That is just incredible. Okay, so having established the rigorous quantum mechanics of a single atom, a single chromium substitution, we really need to zoom back out. We have to scale this up to the macroscopic three-dimensional structure of a faceted gemstone you'd wear in a ring.
Because a polished Alexandrite contains trillions of these highly calibrated, localized fields.
Exactly. And when you examine the bulk material properties of the actual crystal, you hit this concept of Pleochroism, which just adds an immense layer of complexity to the whole thing.
Pleochroism is where it gets really wild for gem cutters. So Chrysoberyl is an orthohommic crystal structure.
Which means its unit cell parameters, the A, B, and C crystallographic axes, are all of unequal lengths.
Right. It's a lopsided 3D grid. Optically, this classifies the material as biaxial. When unpolarized incident light like sunlight enters this orthorhombic lattice, the unequal atomic spacing along those three different axes actually forces the light to split.
It splits into distinct polarized wave components traveling at different velocities.
because the atomic density and the electrostatic fields we just talked about vary depending on which axis the light is traveling down. So the light is subjected to three distinct absorption profiles.
Aligned with the three principal vibration directions of the crystal, which mineralogists designate as X, Y, and Z.
This means the material inherently possesses three separate baseline colors depending purely on the angle you look at it.
Wait, three colors?
Three colors. If you isolate the transmission profiles along those specific axes, the Pleochroism of Alexandrite is really stark. Light traveling purely along the X vibration direction transmits a deep violet or purple color.
Okay, purple.
Along the Y direction, the transmission completely shifts to a distinct yellow or orange.
And along the Z direction?
It transmits an intense blue-green. The stone is literally optically tricolored based purely on the viewing angle relative to its internal crystal grid.
That is insane.
Yeah.
And on top of that directional absorption, the macroscopic perception of the color is heavily governed by something called the Uzambara effect, right?
Yes, the Uzambara effect, which is basically an application of the Beer-Lambert law of absorption.
Which states that the attenuation of light, how much light is absorbed, is directly proportional to the optical path length through the material.
In simpler terms, the physical thickness of the gemstone alters its color.
Right, because a photon traversing a massive 5-carat Alexandrite is going to physically interact with significantly more chromium ions than a photon traversing a tiny half-carat stone.
Exactly. As the path length increases, the cumulative absorption intensifies.
And because of how human eye sensitivity curves work, this exponential increase in absorption causes thicker stones to visually shift toward the red spectrum, even under daylight illumination.
Just because it's thicker, the physical dimensions of the cut are directly manipulating the optical output.
So if you're a gem cutter,
Yeah.
this sounds like a nightmare. This confluence of Pleochroism, the three different axis colors, and the Uzambara effect, historically created what was known as the cutter's dilemma.
Oh, absolutely. Cutters were terrified of ruining these stones. They were highly aware of the three pleochroic axes, and that y-axis transmission, the yellow-orange color, was considered highly detrimental to the value of the stone.
Because it muddied up the crisp green to red color change. Nobody wants a brownish-yellow Alexandrite.
Right. So the standard operating procedure in gemology for decades was to meticulously orient the rough crystal so that the large, flat top facet, the table facet, was cut perfectly perpendicular to the B-axis.
The goal being to force the incident light to bypass that ugly yellow-orange y-axis entirely and isolate the blue-green and purple-red transmissions.
It was an incredibly restrictive geometric constraint. I mean, cutters often had to sacrifice massive percentages of the rough crystal weight just to align the optical axis properly. You'd lose half the stone.
But they didn't actually need to do that, did they?
No, they really didn't. Extensive optical studies, particularly the ray tracing analyses conducted by Carl Schmetzer, proved that this strict orientation was basically a waste of time for modern cuts.
Carl Schmetzer's work is fascinating here.
Yeah.
He analyzed the internal reflection pathways within complex mixed cuts and brilliant cuts.
Right. Because when you apply Snell's law to a highly faceted chrysoberyl, the critical angle dictates that light entering the crown facets, the top of the stone, doesn't just shoot straight through.
It undergoes multiple total internal reflections off the bottom pavilion facets before it ever exits the stone and hits your eye.
In a complex cut, the light ray does not travel along a single linear axis. It bounces obliquely across the internal geometry like a pinball.
And Schmetzer's data proved that these multiple oblique internal reflections basically act as a giant optical blender.
A perfect analogy. Because the light is ricocheting through the crystal in dozens of different vectors, it's simultaneously sampling the X, the Y, and the Z absorption profiles all at once.
So by the time the heavily reflected light finally exits the top of the stone and reaches the observer, those three distinct pleochroic colors are thoroughly averaged together.
The internal geometry of the faceted stone mathematically averages the violet, the yellow, and the blue-green transmissions.
Which means Schmetzer confirmed that as long as the localized chromium concentration dictates the proper 10dq gap, the multiple internal reflections will consistently synthesize the macroscopic green to red color change, regardless of how you orient that initial top facet.
You don't have to sacrifice half the stone to line it up perfectly. The macroscopic faceting harnesses the internal chaos of the pleochroic axis and just synthesizes it into a reliable, consistent optical illusion.
Which brings us full circle. We have traversed from the macroscopic failure of human color constancy algorithms down to the quantum mechanical transitions of a single chromium electron jumping states.
We mapped the non-local electrostatic potentials via density functional theory.
And returned all the way back to the macroscopic ray tracing of a beautifully faceted gemstone. It really is a profound realization that the aesthetic value of this mineral, what makes it so wildly expensive and sought after, is entirely derived from a highly rigorous matrix of physics.
The Alexandrite effect isn't just some arbitrary quirk of nature. It's the precise intersection of black-body radiation curves, the Hohenberg cone theorem mapping internal electric fields, the Lagan field splitting of transition metal orbitals, and the absolute limitations of human visual neurobiology.
I mean, when you observe the color of any material, be it a piece of plastic on your desk or a natural crystal, you have to realize you are not observing a static pigment.
No, you are observing a live, real-time calculation of quantum electron transitions, perfectly constrained by local and non-local electrostatic fields. The physical world isn't just solid objects, it's an interconnected matrix of these invisible forces continuously reacting to ambient energy.
And what's really amazing to me is that this mathematical predictability of the absorption shift isn't just an academic exercise or a jewelry trick.
Oh, not at all. Because the hue angle traversal in that Scilab color space we talked about is perfectly correlated with the spectral power distribution of the illuminant, the effect can actually be utilized as a highly calibrated optical sensor.
Right. I want to leave everyone with this final mind-bending application, the Alexandrite effect spectropyrometer.
Yes. This is such a brilliant application of the physics.
In extreme high-temperature physics like, say, monitoring thermal plasma torches that are operating at up to 6,500 Kelvin direct contact thermometry is physically impossible.
Right. If you stick a physical thermometer into a 6,500 Kelvin plasma torch, the environment just instantly destroys the instrumentation. It melts.
But by utilizing an Alexandrite filter as a spectropyrometer, researchers can mathematically map the hue angle transmission of the plasma's emission spectrum from a safe distance.
Because those localized electron transitions of the chromium ions react to the plasma's specific light spectrum with absolute mathematical precision.
The resulting color shift in the stone can literally be used to calculate the exact operational temperature of the plasma field.
It's incredible. A random trace chemical substitution in a beryllium aluminate lattice, governed by the invisible internal electric fields of distant neighbor ions, is now utilized to mathematically derive the thermal output of a 6,500 Kelvin plasma torch simply by measuring its optical transmission.
Which forces us to completely reevaluate our perception of the solid state. We observe a gemstone and categorize it as a static, inert object, just a pretty rock. But beneath that macroscopic surface, it is a highly volatile, highly calibrated quantum architecture, continuously calculating and reacting to the ambient energy fields surrounding it.
The physics are entirely invisible, yet entirely deterministic.
Well, that's all we have for today. We hope this changes how you look at the physical world, and we'll catch you next time as we keep unpacking the invisible forces all around us.